Hey, welcome everyone to the next day of the conference, Wednesday. So we have a session on tweakable block ciphers with 4 talks. The first one is optimally secure tweakable block ciphers with a large tweak from n-bit block ciphers. It's a paper of Yaobin Chen and François-Xavier Standard. And Yaobin will give the talk.
Okay, thanks for the introduction. And this work was done when I was postdoc in UC Leuven, and now have moved to the Xiamen University. So block cipher and tweakable block cipher are 2 important primitives to design some operation or some building block for more advanced cryptography protocol. And block cipher is the written permutation indexed by the secret key. And while for tweakable block cipher, there's an additional parameter called the tweak. And so for a pair of key and tweak, it will have like a written permutation. And here key is secret to provide a security, and while the tweak is public to provide the flexibility. So that part is the block cipher. The input is the plaintext and the key, while the right part is the tweak block cipher. There's additional parameter called tweak. And there's some approach to design a tweakable block cipher. The first one is the dedicated construction. There's some example like the hasty parting cipher, or mercy, or skinny, or doxy, BC, or the recent one, comma. And the second approach is using the modular approach. We can design TBC directly from a block cipher, like AES. And this approach is generic, and we can also reduce the security of the typical block cipher to block cipher. But the transformation from block cipher to typical cipher is important because we need to just justify why this transformation can be secure. Maybe there's some attack, because maybe all the AES is secure, but if the transformation is not secure, then the typical block cipher will be insecure. So that's why we need some proper security here. So there's some example, maybe show to how to design a tweakable cipher from a block cipher. The first one is the called LORW1. Actually, just the simple concatenating to block cipher and just inject the tweak on the middle of the 2 block cipher. So then we can simply change the tweak. Then we can change the overall construction of the tweakable block cipher. The second one is the LORW2. These 2 are proposed on the same paper in the 2002 in the crypto paper. The second one uses the universal hash function. So actually, you just hash the tweak, then use the hash value as the max to the input and output of the block cipher. So by this way, if we change the tweak, we can somehow change the block cipher to become a tweakable block cipher. And here the assumption is that the hash function should be like almost auxiliary hash function. And these 2 construction, the transformation is busted secure, which implies that after the 2 to the half-n query, the adversary can distinguish these 2 tweakable block cipher from the tweakable random permutation. This is the state of art. Actually, there's a serious work they work on how to design the tweakable block cipher from a block cipher. We can see the first 2 I will introduce a bit, and there's the XEX and the concatenating LORW1, and also the generalized concatenating LORW1, LORW2, and the minimal design XHX, SHX2, and also Mennink design, and also Wang et al. Design in Asian Crypt 2016. But we can summarize a bit. Actually, to support more n-bit tweak, all existing schemes required an additional primitive called the universal hash to compress the tweak. This is a bit tricky because then we need, besides the block cipher, actually we need to another primitive to design the block cipher. So this is starting point about our research. We want to design a large tweak, but without relying on the universal hash and merely using the block cipher. But why we want to go in this direction? Because TBCU is a large tweak, can enable more flexible design. Actually, in the recent year, there are many design. They use the large tree block cipher to design some MAC AED for this encryption. And with the large tree, actually, we can somehow improve the security of the MAC, or improve the security of AED, or maybe it's more convenient to design leakage-resistant cryptography. And so the question is that, can we design a large tree TBC with ambit security from merely a block cipher? So if we have this kind of construction, then it can be efficient when AES co-processor available, and without using the maybe other primitive like the universal hash, and it will be helpful for more flexible design. So here is overview of our construction. We investigate how to design a TBC with more ambit. Actually, we focus on the 2-ambit trick here and ambit security from 2 block cipher cores. I will introduce why we do not begin from 1 block cipher core, but there's a negative result that is impossible to achieve the ambit security with merely ambit 1 block cipher core. And we show all of these constructions suffer from the birthday bound attack. And then we go one step further. We propose a Tweakable block cipher construction called G2. They can supporting a 2-ambit trick with ambit security and from 3 block cipher core. And this is our construction. The design idea is that we use the first 2 block cipher core to divide to internal value y1, y2, and then use the 2 internal value. The first value to mask the input and output, and the second value to mask the subkey. This is the general idea. I will go into detail of our contribution. So let's recall why we began from TBC from 2 block cipher core, because there's previous result that showed TBC from merely 1 block cipher core is at most birthday bound secure. And also there's a result by Wang et al. They investigate that the TBC from 2 block cipher core can achieve the ambit security, but they can only support ambit trick. So the natural question is that, can we extend the block cipher from 2 block cipher core to support a 2-ambit trick? Maybe begin from the work of the Wang et al. And actually, this is the TBC, the framework of TBC from the 2 block cipher cores. So we start to look this framework, whether we can go previously. Actually, the trick here is the same. They just ambit, but maybe we can inject more trick on this position to achieve the longer trick. And as actually as the first we somehow rely on the previous result. So in this Asian crypt paper, they exhaustively found that 5-6 triple cipher can achieve ambit security with ambit trick. So actually, for the construction, they are different from this 56 TBC. We can set if there's 2-ambit trick, we can set this 2-ambit trick the left half and right half to be equal, then it become ambit trick. Then the attack on this paper will apply on this the Tweakable cipher out of this 56 TBC. Then we can merely focus on this 56 TBC to see whether we can inject more trick on this position. And we find only 4 TBC out of these 56. They have 2 positions that can occupy for 2-ambit trick. And this is the 4 TBC we found among these 56. But finally, you find there's some birthday bound attack. The attack is not so difficult. Maybe just change the input and output of the TBC and try to find some collision or even some key recovery attack. But these 2 construction can achieve the more birthday bound security. And then we continue because the first category with the 1 trick dependent key can rely on previous result somehow. But for the second category, actually, we can summarize this the second category into 3 types construction. And the type 3 is trivial and secure, so we only focus on the type 1, type 2. As you can see, actually, maybe simply look at the type 1. Here, the data and data 2 and data 3 are the position to inject the tree. So for these 3 position, the idea is that can we inject 2 m-bit trick on these 3 position, maybe each position m-bit. And the second type is similar, but we then perform exhaustive search and actually find all of these 3 constructions are subject to burst-bound attack. So at this point, actually, we find it's impossible to construct m-bit secure TBC from 2 block cipher core and achieve m-bit security. So we try to consider, can we design m-bit secure TBC from supporting 2 m-bit trick from 3 block cipher cores? But it's a bit hard to perform exhaustive search because the candidate is a bit high. It's 2 to the 34. It's hard to do it by hand. So maybe we try to propose some possible way to design a good one. We recall the idea of previous many one at all to build m-bit trick TBC that can achieve m-bit security. Actually, my idea of the construction can be somehow summarized as follows. The previous time they used the block cipher core with a fixed key to derive an internal value. I used this internal value either as a subkey or a mask for a second block cipher. So then how can maybe we can follow this idea to design a TBC from 3 block cipher core. And so actually the intuition why he can achieve m-bit security is here. If the property to guessing the key of the first BC is the property is p over 2 to the power n, and here p is the number of the ideal cipher query, and the collision between the second block cipher and the ideal ideal cipher query is p multiplied q over 2 to the 2n, and the collision between the second BC and other second BC is 0. Yeah, this is a bit summarized of the how to prove the m-bit security. So we try to follow this idea into how to design a TBC from 3 block cipher core with m-bit security. So maybe we can also use the first 2 block cipher core to divide to internal value, and then use 2 internal value to mask either the input output of the block cipher core and also as a subkey. And we try to find one of the first construction, but this is not a good one. And we find it satisfies the first 2 intuition points, but the third one is a bit tricky because when we write down the equation, when I do the proof, I find actually we can find a pair. The 2 collision can be reduced to be 1 collision, so then the security will become the birthday bound. The detail can be found in the paper. And this is second construction. And actually the previous attack is because there's some relation between the first block cipher core and 2 block cipher core because we simply inject the trick as the input. And so for a second construction, actually we just make a small multiplication. For a first block cipher core, we extra the secret key with the trick. And the second block cipher core keep the same. And by doing so, actually we can break the connection between the first block cipher core and the second block cipher core and avoiding the attack against the first construction. So the previous intuition can be achieved. And we justify our intuition by the proper security method. We use the ideal cipher model. And we prove that actually the G2, the proposed construction, is indistinguishable from checkpoint interpolation with MB security. Here is our theory. Here is MB security construction. So as a conclusion, we show some negative result that we cannot design a TBC from 2 block cipher core with MB security and 2 MB trick. We also show the positive result that we propose a construction G2, that is the TBC built from 3 block cipher core and can achieve MB security and support 2 MB trick. We also have there's a very natural construction to build a MB secure TBC with TMB trick. It requires at least T+1 BC core. This construction is true for the MB trick and 2 MB trick. Maybe it will be true for the 3 MB trick or more than that. Okay, thank you.
Okay, thanks. Any questions? So, Stefan first. Oh, maybe cut off.
Okay, can you hear me?
Yes.
Yes.
Great. Would your negative result also apply when you're looking for more than an n-bit but less than a 2 n-bit tweak, so 1.5 n-bit or 1.9 n-bit or so?
No, I think this is a good generalization for this result. Yeah, because he actually was just focus on the very simple result that n-bit. We always put an entire trick on the partition and achieve the MB trick, MB security. Yeah, I think there should be more flexible proposition like the one you propose. Yeah, I think this will be interesting. Yeah, thank you.
Kazu?
Right?
Yes.
Okay. So your construction used you use the assumption that an n-bit IDR block cipher with n-bit key, right?
Yes. Yes.
Yes. And what will happen if we use route to use the 2 n-bit key for the IDR cipher? Is the problem?
Yeah, I think if we use
or...
the 2 MB key, maybe we can directly achieve MB security. Yeah, but we focus on the MB block cipher with MB input and MB key. Yeah. Yes.
Sure. Okay.
Any other question? I had one small question because given the way you construct it, you always need this ideal cipher model. Do you know a way how you can get rid of this assumption?
You may use the standard assumption?
Yes.
Maybe no.
And achieve the same goal. Yes.
Yeah, I think maybe it's a bit. I remember you have one paper that's to discuss this problem.
Yes, yeah, but maybe you have a solution. I don't know.
Yeah, but I think maybe it's a bit difficult if we want to design and be secure for using the standard model. I do not go into detail for it. I think it's a bit difficult, so I do not go in here.
Okay. If there are no other questions, let's thank you, Ben, again. And then we're heading forward to the second talk of the session. So it's on large tweaks and tweakable Evan Mansur with linear tweak and key mixing. It's a paper of Benoit Colliati, Jordan Eaton, Ashwin Shah, and Sumya Kanti. Saha, and Jordan will give the talk.
Yeah. Okay. Okay. Thanks for the introduction. So this talk will be divided to 4 parts. First, I'll give some introduction on the block ciphers and motivation to our work. Then I'll introduce our construction, the tweakable Evan Mansur with wiki schedule. And the last big part of the talk would be some proof overview of NCCA proof of 2 rounds and some conclusion. So as seen in the previous talk, a tweakable block cipher is simply a block cipher with an additional parameter, the tweak, that brings variability to the block cipher and is usually controlled by the adversary, with the requirement that for each key and tweak, the message maps to the cipher, the function that takes the message to the ciphertext is a permutation. Indeed, tweakable block ciphers have seen a wide range of application as being building blocks of authenticated encryption schemes, messenger authenticated code, and used to attain other security goals. So there are two main ways to design block ciphers. The previous talk talked about designing it from a block cipher in a black box manner, but most of the works that we've seen show that this is either non-efficient or birthday bound secure. And another more recent way to build a tweakable block cipher is from lower level primitives such as permutation. And in this work, we concentrate on designing it from permutation. So a famous paper called the Tweaky framework by John et al. Proposed the design paradigm that builds it from permutations, where they consider the tweak and the key as unified, which they call tweaky, and the schedule is linear. And the high-level design follows the tweakable Evan-Mansour construction. However, no provable security analysis has been done on it so far. So in this work, we aim to provide some provable security footing for the design paradigm. So if we look at the tweakable Evan-Mansour to abstract this, it's simply the iterated version with where in each round we saw some H function on the key and the tweak, and some known results on this tweakable Evan-Mansour is that if the number of rounds is even and this H is XOR universal, it's the TEM construction by Cogliati et al. It's secure up to 2 to the R by R plus 2 times n queries. And for 4 rounds, and when H is linear, it's the TEML construction also by Cogliati et al., which is secure to up to the 2 to the 2n by 3 queries. However, some drawbacks from these known constructions is that it deviates quite significantly from the Tweaky framework, at least for non-constant rounds, and there is no support for larger tweaks. So in our paper, our contributions will be twofold. First, we show that the tweakable Evan-Mansour with 2R rounds, which we denote T2R TML with some alpha and bit tweak, where the schedule follows a property which is called alpha bijective, is in CCA secure up to 2 to the R minus alpha by R times n queries using the coupling technique. And the second result is that tweakable Evan-Mansour with R and bit key or tweaky, and R bijective key schedule in the chosen key model is for R plus 2 rounds, we have an attack, and for R plus 3 rounds, we prove the security. However, due to time constraints, we'll only concentrate on the first result. So now to introduce our construction, the tweakable Evan-Mansour with tweaky schedule. So we just instantiate the previous construction with some functions gamma 0 to gamma R that we want all of them to be linear as in the tweaky schedule. And we know that for 4 rounds n-bit tweak and 2 n-bit key, it's the TML construction by Cogliati et al. So now we want to minimize the number of rounds for some alpha n-bit tweak. So can we have less than alpha rounds? So since the gammas are linear, we can write it as a key schedule XOR tweak schedule. And if R is less than alpha, using simple counting reasoning and some collisions on the tweak schedule, we can derive a collision attack, which I'll not talk about here, but it's quite simple to see. And then we ask if just having more than alpha rounds is enough for security. So we can see that if you choose for 2 n-bit tweak and any number of rounds, we can choose the tweak schedule in such a way that the first R minus 1 rounds have some tweak T1 and the last round has tweak T2, and then we can derive a similar collision attack. So that's not good enough, unfortunately. However, John et al. In the Tweaky framework paper also had similar observation that we have to have some stronger requirement on the tweak or tweaky schedule. So they require that we have some 1-to-1 relation between any pair of key and tweak to some subsets of tweaky, gamma I, KT. And we formalize this notion by the definition of S-bijectivity. So in quickly, an S-bijective schedule is simply a tuple of linear functions where any contiguous S subtuple of these functions satisfy the bijection that we mentioned earlier. So now for the instantiation of our construction, we can simply take a random independent round keys and define the tweak schedule now as gamma IT, which is the Ki XOR delta IT, where delta I is some tweak schedule. And we prove in our paper that for more than alpha rounds, and when this delta is alpha bijective, it achieves in CCA security up to big N to the R minus 2 alpha by R when big N is 2 to the N. So now I will quickly go over the proof in a general overview. So a high-level proof first follows some earlier works. So we make some first simplifications. First of all, if we look at the 2R construction, we can, and some permutations and keys on the tweaks and the inputs of the adversary, we can simply divide it into independent instances of the independent instances of R round by dividing the permutations and the tweaks. So we concentrate on just R round. And the second step is the crucial step. So we have, if we go over the proof, we have we need to upper bound some statistical distance between two distributions. The first distribution is when we look at we fix the keys, and the permutations. We look at all the tweaks and all the inputs of the adversary, and we condition on some partial information of the permutations. And we compare it to some uniform distribution that is dependent on the tweak. So once we have this statistical distance, we want to somehow simplify it so we can analyze it using the coupling technique. So to do that, we define some L hybrids, QC, sorry, hybrids, where QC is the number of construction queries. So the LF hybrid will simply be looking at all the inputs of the adversary, but from the L+1 query, we simply replace the input by something random. And now we can reduce all the problem to just looking at the distance between the L+1 hybrid and the L hybrid, which we call hybrid distances. So to do that, we use the coupling technique. So in the coupling technique, we want to couple this L+1 hybrid and L hybrid. So we start by fixing some QC amount of queries from the adversary that follows the L+1 hybrid, and with the permutations and the keys. And to couple it, we just we will define another instance of the construction where we fix the new permutations and new keys, such that what we want to have is that the output of each the output to the JF permutation at each round is the same for both instances. Of course, this can fail if, for example, the adversary has some previous knowledge on the values of the input to the permutations, and we will analyze with what probability we can have for the coupling failure. So first of all, it's easy to see that we just have to consider just the first L+1 queries from the definition of the hybrids. And we did that so that we can use the coupling lemma. What does that coupling lemma says? It says that the statistical distance of the L+1 hybrid and the L hybrid is upper bounded by the probability that at the end of the two instances, we have distinct output, which means that at some point in the, at some round, the permutation, we fail to couple the two permutations. So the novelty of our approach lies in how to upper bound this probability that the Zs, which are the new instances, the new instance of the construction is distinct from the X. And we call that a coupling failure event. So now we will actually analyze all the coupling failures for the X's and the Z's together, but we just start by looking at only the X's independently first. So the type of collision, the type of coupling failure comes from collision. Obviously, collision events, where we identify two collision events that will be crucial in our proof. The first collision event is actually quite easy. So we look at the L+1 query, and we see that at some point we can have the input to a permutation that is already known to the adversary. We call that a primitive collision. And of course, we can see that with the randomness of the key, we can just bound it by QP divided by n, big N, where n is 2 to the n. And the more interesting event would be the internal collision event, which means that if we have the query L+1 and some query I, we have a collision between the input of some the input to some J permutation. So we further go into detail into how to analyze the internal collision. So we can see that there exists a I query that is smaller than L, such that we have a collision on the input at the JF round between the IF query and the L+1 query. This gives some equation that involves the output of the J-1 permutation for the L+1 query and ith query to be equal to some function h, which is dependent on the tweaks at the ith query, tweak at the L+1 query, and the key at the JF round. And in previous works, that value was actually equal to some XOR of almost XOR universal hash function, which with very high probability was non-zero. However, in our construction, this is because the key cancels out. If we open the equation, we simply have it. We have it equal to some to the tweak schedule on Ti XOR TL+1, which of course can be zero, so that can be problematic. So now we analyze the full internal collision event. So first we assume we have some collision on the input to the JF permutation, and of course there can be a case where delta J in both queries is equal, and then the equation falls back to the J-1 round, and we cannot do anything. So we don't have any probability here. But because of the alpha bijective property, this type of event can only happen alpha -1 times. So we only give up at most alpha -1 rounds for free. Otherwise, let's assume the deltas are not equal. And then in that case, from the equation, we just have to look on the input for the J-1 permutation and look if one of the inputs is fresh. If it's fresh, wonderful, then we can bound it by using the randomness of the permutation. If not, we'll have to open up the equations and go back the rounds until we found some fresh input. So that argument is called a chain argument. And when we stop at the first round, which is the worst case, we call it a complete chain. And when we stop at some round that is not the first round, we call it a partial chain. So the rest of the proof, so in the previous works, they consider the failure at each round independently, and that worsens the bound. In our work, we consider the full event of failing at some round, but together at once. And the rest of the proof is just by analyzing each sub-event and using the probability chain rule. So just an example of how to calculate, for example, the partial chain probability computation. So we assume we have some equality between Yij and YL+1j, and we are searching for some randomness. Let's say it stops. We have some randomness at the round J prime for the J prime permutation, and let's assume without loss of generality that it happens at the ith query and not L+1 query. So the way to compute the probability is first to look at the L+1 query and the input to the permutation J prime +1. Then we can go back the chain using the randomness of the key until we hit the input to the JF round of the L+1 query. And each step of going back is bounded by QP divided by n, where QP is the number of primitive queries. So that's quite easy. That's not anything new. And once we have the equality, we go down the chain from Yij. However, now since the keys are already fixed, we don't have any more probability until we reach the J prime +1 round. And then at the J prime +1, we can use the variable Yij prime, which is the input to the J prime J prime permutation at the ith query, and that gives us 2 over n probability. So overall, we have at most 2qp divided by n to the s, where s is the chain length. So I'll just conclude the talk. So in conclusion, we showed that the 2R rounds of our construction, alpha n bit tweak, achieves in CCA security up to 2 to the r minus alpha by r times n queries. Since coupling is not tight, we conjecture that the same security can be achieved maybe for less rounds. Also, our ideas, which is the looking at all the event together and the chaining idea, can maybe be deployed for other security proofs. And something I have not shown, that in the chosen key setting, we show that r plus 3 rounds are sufficient and necessary for our construction with Rn bit key or tweak key and r bijective key schedule. Thank you for your attention.
Okay, thanks. Any questions? Yes, that's
Thank you for the talk.
Mhm.
And the construction studied in the paper, it uses 2 R independent permutations. Yeah,
R.
R independent permutations.
Yes.
And in the original Tweaky framework, they use the same round function for all the time. If you go back to your Tweaky, you use the same F all the time.
Yes.
And can you comment on the security if we use the same permutation P for all the rounds?
We don't know how to do that, because for the coupling, we actually need the independence of so we don't know how to do it. And also using H coefficient doesn't work because of the type of collision that you can have, for example, for the deltas, for the tweaks. So no, unfortunately for now, we don't know how to do it.
Okay, so what is your expectation? Do you think it still have some security, or you expect that the security will decrease drastically?
I'll have to think about it. I don't know. Sorry.
Thank you.
Thanks. Any other question? So I have a question. It's not on your slide, but could you go to your conclusions?
Yes.
Because you say R plus 3 rounds is sufficient, but I read your paper, and this is, if I understand correctly, you're referring to sequential indifferentiability.
Yes.
Yes. Do you think this is possible to extend this to full indifferentiability?
We were working on that, but with current techniques, it seems very, very hard. Very, very hard. So for now, I don't know.
Okay. Any other question? If not, then let's thank the speaker again. And we're moving on to the third talk of this session. It's a talk, Cascading 4-round LRW1 is Beyond Birthday Bound Secure.
So
It's a paper of Nilanjan Datta, Shreya Dey, Abhijit Dutta, and Sugata Mandal. And Shreya, I hope I'm pronouncing it correctly.
yes.
Okay, great. We'll give the talk.
So thank you for the introduction. So let us start with some brief introduction on Tweakable Block Cipher. So Tweakable Block Cipher is a variant of block cipher. It takes as input a message of length n, a key of size k, and a public value called a tweak t, and it will output a cipher text of the same size as message. So note that this tweak t is controlled by some adversary A, and for each key and each tweak, E tilde is a E tilde kt is a permutation of a 0 to the power n. And if we only fix the key, then E tilde k is a family of permutations indexed by the tweak t. Now to model the security notion, suppose we have an adversary A. Suppose we have an adversary A who has access to some oracle. The oracle can be a tweakable block cipher or can be a tweakable random permutation, but adversary does not know that. He can only query to the oracle. So it queries with a message M and a tweak T and get back a ciphertext C. So after finally many queries, if the adversary cannot distinguish between between these two oracles, then we say that this tweakable block cipher is a secure tweakable pseudonym permutation. Additionally, if the adversary has access to some inverse oracle, and again the adversary fails to distinguish between the real and ideal oracle, then we say that tweakable block cipher is a secure, strong tweakable pseudonym permutation. So now to design a tweakable block cipher from a block cipher, classical block cipher, we have basically two approaches. In the first approach, tweakable block cipher are designed from a classical block cipher with the assumption that the underlying block cipher is a pseudo-random permutation. And in the second approach, we have assumed that the underlying block cipher is an ideal cipher. So here we are basically focusing on the first approach. So the first secure design of tweakable block cipher was observed in LRW1 construction, which was proposed by Liskov et al. In Crypto 2002. The authors have shown that this construction achieves tight CPA security for up to 2 to the n by 2 queries. And one thing is to note that this LRW1 construction cannot be secure against any CCA adversaries. Surprisingly, until the year 2020, there was no extension on LRW1 construction. First in Eurocrypt 2020, Bao et al. Have extended LRW1 to 3 round, that is 3 round cascading LRW1, which is popularly known as TNT construction. And the authors have shown that TNT achieves CCA security for up to 2 to the 2n by 3 queries. In the same year, in Asia Crypt, Guo et al. Have also shown that the 3 round cascading LRW1 with respect to 3 independent random permutation achieves tight CPA security for up to 2 to the 3n by 4 many queries. Additionally, in DCC 2022, Zhang et al. Have extended the cascading LRW1 to R round, which is CLRW1R, and that achieves CCA security for different number of queries depending on whether R is odd or R is even. So it achieves security up to 2 to the R minus 1 times n by R plus 1 many queries when R is odd, and R minus 2 to the R minus 2 times n by R many queries when R is even. Interestingly, Khoiralla has archived a paper on 3 round cascading LRW1. In that paper, he has presented a birthday bound CCA distinguishing attack on TNT construction. And recently, Jha et al. Have also presented a CCA distinguishing attack on this construction. But these two papers differs only in the analysis of the distinguisher, but the claim is same. Their claim is TNT cannot be secure with birthday bound queries. So the security claim of Bao et al. Now stands invalid. So this is the current scenario regarding the cascading LRW1 construction. So 3 rounds LRW1 achieves tight birthday bound CCA security. For 4 and 5 round, we can use the general R round result for cascading LRW1. So putting 4 equal to 4, putting R equal to 4, we get birthday bound CCA security, and putting R equal to 5, we will have the beyond birthday bound CCA security. But this security bound for Zhang et al. Is not tight due to the coupling technique. So there is a clear gap between the security bound of 4 round and the 5 round of CLRW1. So this actually motivates our work. We are basically looking for an answer to some question that is the birthday bound security of CLRW1 can be extended to achieve beyond birthday bound security, or is there any birthday bound CCA attack on this construction? So to answer this question, we have shown that CLRW14 is secure up to 2 to the 3n by 4 CCA queries, and it confirms that at least 4 rounds is required to achieve the beyond birthday bound security. One thing I want to mention here that concurrently to our work, Jha et al. Have also independently shown the 3n by 4 bit security of this construction CLRW14. So this is our formal statement of our security result, where this error term indicates that our bound is order of 2 to the 3n by 4, where the Q is the number of queries. So to prove this security result, we have used a well-known method, which is H coefficient technique, coupled with some results for mirror theory of tweakable random permutation. So given a system of equation, mirror theory is a combinatorial technique that estimates the number of solutions to the corresponding system of equation. So L is the given system of equation, where the variables y1, y2, yq, and w1, w2, wq are the unknowns, and the ti's are the known values. Now we will construct an H-level bipartite graph corresponding to this system of equation, whose vertices are y1, y2, yq, and w1, w2, wq. Now we will put an H between yi and wi with the label ti, and march two vertices yi and yj if they have the same values. And we can do the similar thing for w values also. So we will call a graph is a bad graph if the corresponding graph does not contain any of these 4 conditions. So a bad graph contains a path of length at least 4, or it will contain a cycle, or there is an even length path with sum of their labels is 0, or the size of any component of the graph is at least 2 times q to the power 2 by 3. So now we will call a graph to be a good graph if the graph is not bad. So in this context, Jha and Nandi have studied this kind of equation graphs and have given a lower bound on the number of solutions, to the associated system of equation for a good graph. And we have used this bound in our security analysis to calculate the ideal interpolation probability. Now I will try to briefly sketch the proof of our security result. So the first obvious step is to replace 4 block ciphers with 4 random permutations. We can do this because these 4 block ciphers is a pseudo-random permutation, and our target is to upper bound the advantage of this construction, which is CLRW14P. And we will do this in STPRP security model, which we have already discussed before. So after the interaction is over in the security model, so the challenger will reveal some transcript. So a query response transcript will looks like a message mi, a tweak ti, and a ciphertext ci. Additionally, challenger also reveals the intermediate variables x, y, u, v, w, and z. But in real world, these are the actual values. In ideal world, the challenger does not have the actual construction. So he will have to sample the intermediate variables with maintaining permutation compatibility. So first he will sample these x and z values without replacement, and then set y and w as y equal to x dot t and w equal to z dot t. Now it will only remain to sample u and v values. So depending on this partial transcript, now we will construct an H-level bipartite graph whose vertices are y1, y2, yq, and w1, w2, wq. We put an H between them with the label ti and march 2 vertices even if they have the same values. So now we will call a partial transcript is bad if the corresponding graph is a bad graph. So for a bad partial transcript, we will sample u and v value degenerately. So remember that we will call a graph to be good if it is not bad. So it will have to satisfy the following properties. So the properties are: every path in the graph has a maximum of length 3, and it has no even length path such that sum of their labels is 0. And the graph contains no cycle, And maximum component size in the graph can be at most 2 times q to the power 2/3. So each component of a good graph is either an isolated edge or a star, or it can have a length of at most 3. Now to sample the U and V values for type 1, type 2 and type 3 component, for the queries belonging to these 3 components, we will consider a system of equation Ui is or Vi equal to Ti. So suppose S is the solution set of this system of equation such that the permutation compatibility of Ui, V and W will be maintained, and we sample U and V for uniformly randomly from the solution set S. Now to sample U and V for the type 4 component, we will select an edge in such a way that degree of both 2 vertices is at least 2. Now we sample Ui corresponding to this Yi uniformly randomly from 0 to the power n, then set Vi as Uis or Ti. So due to sampling UV in this way for type 4 component, there may have some permutation incompatibility. As for example, you can see that if the uniformly sample value Uj for type 4 component corresponding to Yj value can collide with already sample value Ui for any one of type 1, type 2 and type 3 component. So one thing you can see that this Yi and Yj are belonging to 2 different components. So obviously Yi not is equal to Yj. So this should be equals to that Ui equal to Uj. But here Ui not is equal to Uj, but here Ui equal to Uj. So this gives the permutation incompatibility. So the similar thing we can done for 2 type 4 component also. And the same thing can happen for the corresponding V values also. So now we formally define 2 bad sets, that is U call alpha beta and V call alpha beta, that captures this kind of collisions of U and V. So the final bad event is bad set, which is basically the union of all possible U call alpha betas and all possible V call alpha betas. So according to H coefficient technique, the final part is to lower bound the ratio of the real to ideal interpolation probability for any fixed good transcript. So in real world, we only have to count the number of times each permutation is invoked. And in ideal world, for type 1, type 2 and type 3 graph, we have used mirror theory result for tweakable random permutation from Jha Nandi in JOC 2020. And for type 4 components, since we will sample one value uniformly randomly from each component, so we will only have to count how many components are there. So this completes the proof, but before wrapping up, we will see some open problems. So in this paper, we have shown that CLR-W14 achieves 2 to the power 3n by 4 CCA security for 2 to the 3n by 4 many queries, but we do not know this bound is tight or not. So it will be interesting to see, to find a matching attack on this construction. And another one is, I have already mentioned that the security result of Zhang et al. For general R round is not tight due to the coupling method. So it will also an interesting open problem to look for a tight improved security bound for R greater equal to 5. The last one is in another direction, it will be also interesting to explore the multi-user security analysis of CLR-W14 construction. That is, we will have to analyze that the single user security bound will remain same in multi-user setting, or it will degrade with the increased number of users. Thank you for the attention.
Okay, thanks for the presentation. Are there any questions? Yes, Kazu.
So thanks for the nice talks. So my question is about the kind of the future direction. So you proved that the 4-round is achieving the 3n over 4-bit security.
Yes.
And the previous result, TNT, is a 3-round one, and claiming the 2n over 3-bit security
Yes.
was wrong. And
Yes.
so my natural question is that whether there's a gap between the 3 and So do you think that is it possible to get a more efficient construction than the 4-round cascaded to achieve the 2n over 3-bit security rather than 4n over 3? Do you have any comments on that direction?
Can you repeat this one?
Okay, so you get an 3n over 4-bit security via 4 rounds,
Yes.
right? But can you imagine that if you can do some consider more efficient construction that achieves only the 2n over 3-bit security?
Okay, then I have to think about it.
Yeah, and 3 round is failing, so does not meet satisfy that goal. So it sounds interesting to me. Yeah, that's a comment.
Yes, there's a weird gap between 3-round and 4-round, like birthday bound and 3n over 4. I think the same holds for LRW2, because I had a question for LRW2. There has been similar bounds.
Yes.
How does this compare with LRW2? Your results?
LRW, can you repeat this?
So LRW2, so you had the Liskov et al. Had 2 constructions. The other one was LRW2 with a universal hash function.
Yes.
Which is often considered cheaper or more efficient. I'm not exactly sure, but they make less block cipher calls.
Okay.
And they get the same bound with fewer block cipher calls.
Okay, to reduce the block cipher calls in LRW1, the Liskov et al. Already showed the LRW2 construction. There is reduced block cipher calls as LRW1. So what is your question?
So how would your result of LRW1 compare to the results of LRW2? Because you make more block cipher calls, but less hashes, right? So
Yes.
is it beneficial or is it more expensive?
I don't know much.
Okay,
about it.
never mind. Yes. Any other questions? So if not, then let's thank the speaker again.
Thank you.
Then we're heading on to the last talk of this session. It's building PRS from TPRPs beyond the block and the tweak length bounds. It's a paper of Won-Sok Choi, Choi-Young Lee, and Jung-Min Lee.
Is it work? Okay,
Yes, it's working. Go ahead.
Yeah, okay. Let me start my presentation. So actually my family name pronunciation is Choi, but I don't know why these Korean guys write my family name in this way. But okay, let me start. So let me first introduce about more something I talked in the RAM session and give some brief idea about Tweakable Block Cipher and what we did and what is the technical contribution and some application and conclusion. Okay, because we already have 3 very good presentation on Tweakable Block Cipher, so I want to start with some different problem. So this Ruby Lego problem is starting from 1970s. So at that moment, Feistel and Cooper-Smith designed the IBM's Lucifer Cipher using Feistel network. And Ruby and Lego first assume their inner round function is a secure pseudo-random function. And by assuming this, they can prove 3-round 5-tail structure is actually a secure pseudo-random permutation. And if you do that on 4 rounds, then it becomes a strong pseudo-random permutation. So the Ruby record problem basically asks us how to make secure PLPs from secure PLFs. But nowadays, we are more familiar with designing block cipher than actually PRFs. So we have AES and many Tweakable block cipher that introduced in the previous papers, previous presentations. So, and block ciphers is typically modeled as a PLP in the standard model, especially. Meanwhile, hashes, MAX, or AEADs prefer to use PRFs, at least implicitly in their security groups, to especially when we want to achieve beyond birthday bound security. So Ruby backward problem now asks us how to make secure PLFs starting from the secure PLPs. So what is the secure pseudo-random function? So let me first define this one before go further. So let's say C is our dream construction. Takes a key input and message input and output some ciphertext or tag or any kind of output. Then the advantage of some adversary in breaking the PRF security of this construction can be defined as a security game to distinguishing the real world and the ideal world, where this ideal world is a truly random function. And we, in information theoretic setting, we define the advantage of this PRF security of this construction as the maximum of all possible adversaries advantage over all the distinguisher against C, making at most 2 queries. So this is one of the most common idea how to make a PRFs from the PLPs. So you can use the same input to 2 different permutation and XOR of the outputs. In this way, we can obtain an n-bit secure PRFs, and it is actually tight n-bit secure trivially because if you make the all n-bit input and XOR all the output, then it becomes 0, while the random function may not be 0. And then let me briefly talk about Tweakable block cipher more, because I expect you already get some Tweakable block cipher idea of Tweakable block cipher from the previous 3 presentations. So I'll just give a very short introduction. So Tweakable block cipher, of course, takes an extra input called tweaks. And actually, these tweaks help us a lot, very useful. So it provides many variability to the block cipher. So by using these tweaks, we can make much easier to design various high-level cryptographic scheme like MAX and AEADs and more. So we assume this tweakable block cipher as a tweakable uniform random permutation. If we use tweakable block cipher as a primitive, and if we want to build something, the bigger construction using tweakable block cipher, then we want to idealize this tweakable block cipher. So tweakable block cipher is behave like an independent random permutation for each tweak. So we call it as a tweakable permutation. And this ideal counterpart of TPLP is called a tweakable uniform random permutation, or TULP. So actually, we assume TULP in the real world and using this TULP to build a bigger construction. But yeah, conventionally, I don't know why, but in many cases, we just say TPLP instead of TULP. So here, I will just say TPLP in this slide. So then the natural question now follows how to build up PRFs from TPLPs. Now we have a Tweakable block cipher, and then how to achieve a good PRF security construction. So actually, it is very easy to achieve n-bit PRF security using a TPLP. Actually, not n-bit, but optimally secure PRFs just by fixing message and only varying this tweak. Yeah, here is the answer. By fixing message and varying tweak inputs, we can define the fx in this way, just for some random fixed C. Then we can obtain a just optimal secure pairs, just the advantage will be 0. However, the input domain is limited up to, yeah, this is typo. Because we only varying the tweak input, the input domain is limited up to 3-bit string. But ideally, TPLP-based PRF may achieve n plus T-bit security because each input domain is the tweak and message input. So the total input size is T plus n, and each input, there is some randomness. So it is just conjecture, but yeah, we can easily expect it may be possible to achieve the optimal n plus T-bit secure PLFs using TPLP. But we don't know how. So how about using 2 TPLP? Let's think together. So in this slide, we only consider T equal n cases. And actually in the paper, we consider more general cases, but here, let's do it simple. So we first consider XOP-like construction, which we call MXOP, defined in this way. So MXOP takes 2 n-bit inputs and using 2 TPLPs, and we divide n-bit and n-bit, x and y, and just y becomes tweak and x becomes input message. So actually, this is the same as a multiple instance of XOP by regarding this tweak part as a security input for each instance. So this is just a multi-user security of XOP. So this security just being reduced to that of multi-user PRF security of XOP, and it will be n-bit secure. And actually, the most recent result from DNode in Eurocrypt 24 will be published, will be presented. So MXOP can be secure up to the 3n by 2 queries if one is limited to query for each instance. Then the adversarial advantage is also bounded by this number. However, when I write this paper, the most tight bound of MXOP was known to be this number. But actually, by fixing a half of bits of messages, actually we can achieve a same security level in this number. So by fixing this some part of message, the previous bound is also can be reduced to this to the 1.5 n bit. So 1.5 n bit input space, it achieves a 1.5 n bit security, and we call this construction MXOP under n by 2, where n by 2 indicates we fix n by 2 bits part of messages. And now we propose a new construction. We name it as a XOTP. So XOTP defined in this way. So we get the same 2 n-bit input, and in the first TPLP, we use Y as a tweak, we use X as a tweak in the same as the MXOP. But for the second TPLP, we use X as a tweak and Y as a message input. So we swap X and Y in the second TPLP. Just by simply swap in this message and tweak input, we can actually achieve a better security bound. So for more detail, we also define the XOTP under C. When we fix some part of message input, it looks a little bit complex, but yeah, it actually simply swap the message and tweak input but message and tweak space is now not the same if we fix some message parts. So just remain some C and W in the same tweak and messaging, but we swap the most bigger part, the M-C bits of X and Y is swapped in this way. So And XOTP-C still outperform MXOP-C, even together with the recent breakthrough of dinner. So still XOTP is useful. And our security claim of XOTP is here. So the PRF security of XOTP is upper bounded by these terms. In particular, by defining C equal n by 3, we obtain a 5n by 3 bit to n bit random function, which is 5n by 3 bit secure. And this is the security comparison between the XOTP and MXOP, which I have to say that I drew this graph before I know the recent dinner's paper. So yeah, so this thin line is the security level of XOTP is on the top of MXOP. So how to prove this security claim? So we have to use mirror theory as introduced in the previous slide, actually. So this mirror theory basically lower bound the number of solutions to some given system. And what is the system? We define a random variable P and Q. There are small q number of P and small q number of Q. And we define some constants Z's. And we have these linear equations, gamma. And then we want to count the number of all possible solutions to this gamma system. But how to do that? Expectedly, if we fix the P and Q just by random, then the probability that P plus Q being Z will be 1 divided by 2 to the n. So roughly, just number of choice of P times number of choice Q will be always have the satisfy this equation with the probability of approximately this number. So the total number of solution we can expect will be approximately in this number. So in this number, we hope the expected number of solution will be similar to this number. And the mirror theory actually proved the lower bound of the number of solution is similar to this number. So this system of equation, to make easy the understanding, we can represent it as a simple graph C by making those random variable as vertices, and each equations denoted by each edges, and each edges contains a label with this constant C. And we define some variable Zymax, which denote the size of the largest components, but in our paper, we will only consider Zymax is equal to 2. So this is the example of graph representation. When Zymax is 2, the graph is beautiful, while Zymax become large, yeah, I don't know, but we don't consider this graph. So, but in our TPRP cases, the problem is a little bit tweaked, because variables from TPRPs are necessarily distinct. So in this system of equation, if these variables comes from the same permutation, those should be distinct. But in our case now, it may not be distinct. So how to deal with this problem? This is the main contribution of our paper. So we divide each part of the set of variables. And what this means? If the two variables in the same set, then it implies these two variables comes from the same tweak. It means that comes from the same permutation. So it should be distinct. Otherwise, it does not have to be distinct. So we can denote it as a relation between the indexes of two variables. So if I and j have a p relation, it means that the pi and pj from the same permutation, so it should be distinct. And then we define some variables using this relation, and we obtain this theorem. So maybe you don't want to understand this theorem during this slide, so let's skip it. And this is the history of mirror theory. There are a bunch of tries to improve mirror theories. And our work is the first work to be able to prove some construction which can be secure beyond the ambit security. So this is the possible applications. To be honest, our using two TPRP to make a ambit PRF might be inefficient. So this is the more like proof of concept applications. But yeah, we can do a bunch of things if we have a strong primitive. So let me explain more. So hashed-and PRF paradigm for constructing max is very useful because we need a variable length message mapped onto some fixed length variable through the weak primitive called hash function, and then we want to encrypt using a strong primitive normally using PRF. So there is already some known TBC-based construction and using two TBC calls at the finalization step. So there is a PMAC TBC version and PMAC X, which achieve ambit security, and ZMAC, which also achieve ambit security. So basically, it is very hard to go beyond an ambit security. But if we use XOTP as the finalization, and then we can achieve like this complex number of security level. And as a CTR counter mode type of encryption, we can use nonce as a twig input, and by using a block counter as a block cipher input, then we achieve normally one can achieve this kind of security level. But if you're using a XOTP, then one can achieve actually a better security level. And another numerical example, if we use a skinny 64.192 with 128-bit security, then actually using XOTP, one can build like beyond 100-bit secure random function. Even this skinny function actually takes a 64-bit message and output 64-bit ciphertext. So this is the last slide. So what we did, making beyond the block and twig length secure construction called XOTP, and we developed mirror theory to prove its security. And future research is, of course, doing more tight analysis of XOTP. And I expect if we can make a relaxed version of mirror theory of Zymex larger than 2, then we can propose a more construction which is more secure or even more efficient. And then, yeah, this is the end of my presentation. Thank you for listening.
Okay, thanks for the talk. Any questions? Yes, Stefan.
Calling two independent tweakable permutations is a little bit expensive.
Yeah.
Would your techniques apply when you have one tweakable permutation and one PRP, and do something like PRF of XY is tweakable PRP of XY, X or PRP of Y, where the first X goes into the tweak?
Oh, actually, I never think about it, but that's really very interesting question. So actually, I was very struggling to convincing reviewers why we have to use a TPRP to build PRF. So if you already have a PRP, then you can just using PRP. That was the common comments I received. So I didn't think about it, but yeah, I think that's definitely very interesting. So yeah, but yeah, I don't know how to convince the reviewer, but yeah, I want to think about it more actually, but I'd never think about it before. So yes, so no intuition right now, but that's very interesting.
Thanks.
Okay, any other question? Kazu?
So regarding your you mentioned that about the renewal recent result about to be presented at the Eurocrypt 2024.
Yeah.
And yeah, so is there any Yeah, what's the real difference? I mean that your result is purely improvement over the deneuvered result, or there are some difference or additional result?
Yeah, there are some different because where was it? So the deneuvered result is this. He proved this security bound, while we proved this security bound. So actually, this one is the strongest one. But in this paper, we tweaked this construction like by adding some constant in the message. Like in this way, we can obtain some little bit different security levels. So yeah, this is the some different point of view.
Thank you. And sorry, an additional question. So you mentioned that about the application side that ZMAC could be improved with the security if it uses your construction for the finalization.
Yeah. But yeah, because we don't have a good hash function, so this is also kind of open problem actually.
Hash function, you not a primitive, but
yeah. So if we assume there is a good hash function which output the P plus n minus L bit, then yeah, we can do it.
I see. Thanks.
Okay, thanks. We're slightly running over time. I think the coffee is waiting for us. So let's thank Wonsock and all the other speakers again.
Oh yeah.